This is my first time here. It's in fact my first time in Portugal, surprisingly. This is going to be really weird seeing myself on the TV. So I apologize for being a few minutes late, but you can thank Air Portugal for that. So, thanks, that's great. Okay, so I'm going to talk about some work that I completed last year in collaboration with Dionysios Milanos, who's my student in Edinburgh, and with Peter Schuch, who's in Bremen. Peter's an expert on deformation quantization, and he did a sabbatical in Edinburgh last year, so it was good timing. This is a very much a string theory inspired talk, and I see that this is a joint string theory geometry seminar, but I think the technical details at sort of both ends on the mathematics and the string theory side are kept to a minimum, so hopefully there's some happy compromise. So what is this talk about? I'm going to just spend some time sort of motivating what I'm going to talk about and also give a bit of background about what's known. So the idea is that one of the things that inspires mathematical physicists, such as myself, is what we call string geometry. And this is just based on the notion that strings, because they're extended objects, they see geometry or they probe geometry much differently than point particles do. Okay, and there's a long list of examples of this, but what's particularly relevant to this talk are notions of target space dualities, and in particular, non-geometric backgrounds. So I'm going to tell you what these non-geometric backgrounds are, but they're intimately tied to notions of T-duality. Okay. Now, of course, another motivation for studying string theory is that at least for closed strings, we hope that closed strings can serve as some probes of geometry or space-time at very short distance scales. Okay, so maybe it could be the Planck scale, it could be whatever your favorite scale is, but whatever that scale is, we know that there's going to be a limit on the resolution of distances that we can measure. And it's hoped by, in particular, people who study non-commutative geometry that we can think of space-time geometry at the Planck scale in terms of some non-commutative structure. Okay, so and this has been work I've been actively involved with over the years in trying to understand aspects of string geometry using the mathematical language of non-commutative geometry. So the question is, can we see these types of non-commutative structures, for example, coming out in string theory? This was a long-hoped goal, and it wasn't realized in a systematic way until around 14 years ago, when in the context of open string theory, it was noticed that non-commutative spaces, non-commutative geometry, arises very naturally when you think about D-branes in certain external fields, in particular B fields. Okay, so if you're not a string theorist, you might not understand this, but this is just to sort of get going where non-commutative geometry is popping up. So the low energy dynamics of the D-branes in string theory in certain setups in a limit is described by a non-commutative deformation of standard Yang-Mills theory. And many works related these non-commutative theories to ordinary theories using technology of things called Seibert-Witten maps and so on. Okay, so this was the sort of status 14 years ago. So why does non-commutative string geometry come about? Well, again, we're talking about the open string setting. So the simplest open string is the world sheet is a disk. Okay, so it's got a boundary. We look at the two-point function on the boundary of that disk, and we want to ask, can we calculate some kind of target space non-commutativity? And to talk about a well-defined target space object, what we mean here is something which is independent of the world sheet coordinates. And it turns out that for the two-point function on the disk in a B field, there is a certain limit where that correlation function depends only on the ordering of points along the boundary. So that's a well-defined target space object, and you can use that correlator to calculate the commutator of two string fields, and you find that you get a non-commutativity relation between the string fields. And what's deforming the commutator string fields is this background B field. This is a two-form field in target space. Okay, so there's a non-commutative two bracket. I'm writing two bracket because we're going to have three brackets in a minute. And then, so then, over the past 14 years, there's been a tremendous amount of work developing what the low-energy effective field theories look like, and the quantization of this produces star products of fields. This is the way physicists like to think about quantization of things like that, in the sense of deformation quantization. Okay, now that's the open string setup, but open strings are not going to probe space-time geometry. If you see geometry, we have to go to the closed string sector. So it wasn't that long ago when these people here, this group in Munich, asked, can you see some kind of non-commutative structure in the closed string sector? So again, you have closed strings, so now our world sheets, our Riemann surfaces are closed surfaces. And the simplest analog of the disk for a closed string is a sphere. If you calculate the two-point function of closed string fields on a sphere, this is not a well-defined target space quantity because it does depend on the world sheet insertion points of the string fields. However, if you calculate the three-point function on the sphere in a certain limit again, you find that it depends only on the relative orientation of the 3 points and not their precise location on the sphere. So that is a well-defined quantity, and you can ask, what does this three-point function measure? Well, it's some kind of three product, or rather a three bracket, which we think of as giving a non-associative structure. So we imagine that we've got a binary product of our fields. You can calculate the associator, which would usually vanish for an associative product, but here it doesn't vanish. So this is not just a non-commutative structure, it's also a non-associative structure. Okay, and the non-associativity is controlled by this three bracket. Okay, so that's just I'm going to go into this in a bit more detail later on, but this is sort of the inspiration behind this talk, because once the last point up here was that we understood how to quantize this two-bracket structure you get in the open string sector. The question is how do we quantize this three-bracket structure? And this is not known. This is new techniques of quantization. So this is what the project was about, was to understand that. And there are many different ways to understand these non-associative structures. So what I'm going to talk about today, or what I'm going to call dynamical star products, they have a very sort of physical and heuristic feel for why non-associativity arises. But then there's many more formal ways to think about this. You can think of these three-bracket structures as being a violation of a Jacobi identity for a Lie algebra. And the natural way to think of that is to think of this as a Lie 2 algebra. So this is a categorification of the notion of a Lie algebra. And so you get a notion of a categorified quantization and so on. You can, if you're into twist deformation techniques, where you can usually understand standard deformation quantization by doing a Drinfeld twist quantization. There's a generalization of that as well, where instead of using a Hopf algebra of symmetries to deform your algebra of functions, you use a quasi-Hopf algebra, and the quasi again refers to a loss of co-associativity of the coproduct in the Hopf algebra. So I may mention these at the end if I have time. I probably won't. But this is really what we're going to focus on. And if I have time at the end, I'll also talk a little bit about how you can think about Seiberg-Witten maps in this framework, where now we map between non-associative and associative theories of gravity. Now, the interplay between non-commutativity, non-associativity, and gravity in string theory is not new. It hasn't appeared in the context I just described. Non-associative gauge theories and open string theories have been observed before, because if you look at non-constant B fields, so the B fields that have a non-vanishing free-form flux, these give non-associative structures because the B field should play the role of some kind of symplectic structure, and this is a violation of the closure condition you need for a symplectic structure, and it implies a violation of the Jacobi identity for the corresponding Poisson vectors. Okay, so that's a well-known scenario. And there's also a well-known way to think about how to quantize these theories using the notion of non-commutative gerbs. So you've got a non-zero free-form there. You can think that's a representative of the characteristic class of a gerb. So that you can describe gerbs in the check picture, split up your manifold into patches, and in each patch you can describe these things using associative algebras. And the whole non-associativity comes into play when you start patching things together. So that's some well-known work from some time ago, which actually the offspring of this was actually a lot of work on non-abelian gerbs. And I don't know the literature that well, but as far as I know, this work by Ashkenazi and company on this deformation quantization inspired a lot of the mathematical work on non-abelian gerbs. So the non-associativity has been there in the open string picture, and deformations of gravity have also been considered. Okay? There's a well-known way to think about differential geometry on non-commutative spacetime because you take the generators of diffeomorphisms, these are vector fields, they form a Lie algebra, and the universal enveloping algebra of that Lie algebra is a Hopf algebra. Once you've got a Hopf algebra in the game, you can deform the Hopf algebra in a compatible way that you've deformed your space-time, and you get a notion of twisted diffeomorphism invariance. It's kind of a deformed diffeomorphism invariance. So there's a well-defined way to do this mathematically, to think about differential geometry and to study Einstein's equations and non-commutative analogs of Schwarzschild solutions and things like that on non-commutative spacetime. However, these symmetries do not arise in any physical sense in string theory. So if we want to kind of focus our attention to things that come naturally out of string theory, this again is not the thing we're looking for. Okay, so let me mention what non-geometric flux compactifications are. So I'll just give an example of how these come about. So the standard example of non-geometric backgrounds comes about, you take a three-dimensional torus and you put a free-form flux on it, a constant free-form flux. Okay? And what we're going to do is we're going to apply T-duality transformations in succession around each of the three cycles of that torus. Okay, I'm not going to tell you what the rules are, but there are well-defined Buscher rules for how to transform the fluxes, B field, the metric, and so on. Okay? So what happens, we start off with just the standard H flux. This is a well-known geometrical background. Again, as I mentioned, you can think of the H flux as a representative of the characteristic class of the gerb. So, we know how to deal with that well-known geometric thing. Now we apply a transformation along, a T-duality transformation along one of the cycles of that torus. Okay, so I raise the index on my tensor every time I do T-duality. When I do that, I still have something that's geometrical. You can describe this explicitly. It's something called a twisted torus, which is an example of a Heisenberg-Mill manifold. Okay, and the H flux now becomes this metric flux, which is described by this Cartan-Mauro type equation for a choice of elements for the geometry. Okay? It's still very geometrical, but now we apply another T-duality transformation to a second cycle, and now things get interesting, because now we start leaving the geometrical world, and we end up with something that in this case is called a T-fold. Okay? So these are non-geometric backgrounds. They're locally geometric because I can patch up my three torus, and in each patch think of it as just a conventional Riemannian manifold. But when I glue the patches together, the transition functions do not only involve local diffeomorphisms, but they also involve string duality transformations. So they involve also T-duality transformations, and that's why they're called T-folds. Okay, so this is the classic example of a T-fold. non-geometric background. We call the flux a Q flux, so it's got the two raised indices, and it was suggested in the open string context many years ago how to think about T-folds in the language of non-commutative geometry. So it was suggested that exactly this T-fold can be thought of as a fibration of non-commutative two tori over a circle. Or if you more precisely, it's a continuous field of non-commutative tori. Okay? So if the base of the circle here is one of the x coordinates, then you see your B field here is given by one of these, is proportional to one of these x coordinates, so it's controlling the non-commutativity of the fiber directions. That's the way to think about this. Okay? So for each point on here, I write down this deformation parameter, and that gives me a non-commutativity in the fiber. Okay? And that could be made very precise and studied using all kinds of formal technology. The things we're going to look at today, though, are when you take a third T-duality transformation, and now things just become a total mess. The problem with doing a third T-duality transformation is that in order to apply the Buscher rules for T-duality, you need to do T-duality along an isometric direction. Okay? But the third, once you're in this situation, the third direction that you want to do T-duality to is no longer an isometric direction. So in principle, you're not even supposed to do T-duality there. Why do people talk about it then? Well, because in their arguments from string field theory, that suggests that still we should include such backgrounds in our wardrobe of consistent string theories. Okay? But these are a mess. Okay? They're not even locally geometric. So I can't even think of them as patches glued together with some transition functions. And again, some years ago, it was suggested that these R-flux backgrounds could be thought of as some kind of non-associative tori. Okay? This is a bit different from the non-associativity we're going to talk about today, because these arguments here are based on an open string picture. They're actually using K-theoretic methods. That's why I call this topological here, because there's no geometry in the description of these. They really just look at K-theory classes. They were thinking about D-brane charges. Okay? And we don't want to think about just topological things. We really want the full-blown machinery of T-duality here. But the point is these structures were noticed many years ago, and now it's just coming back in the context of closed strings. Okay, so how do we deal with non-geometric backgrounds? Well, there are several ideas. A common framework is generalized geometry, right? Where instead of we think of not just fields as sections of either the tangent bundle or the cotangent bundle, but we consider them simultaneously. Okay, so that's, and you can there are techniques to generate these non-geometric R fluxes, the things I wrote down on the last overhead, by taking T-duality transforms of sections of this generalized tangent bundle. Okay? This generalized tangent bundle is going to play a prominent role in this talk, although we're not going to think about it in terms of generalized geometry, but we're going to think about it as a Courant algebra. We'll come to that very soon. Another common approach to non-geometric backgrounds is through double geometry. You take the coordinates of space-time and you double them up to include the dual coordinates. Okay, so T-duality now is manifest in this double geometry. It's just exchanging coordinates with their duals. And then the key thing is whenever you build a field theory on this double geometry, you have to implement some projection which projects out the dual coordinates, because the dual coordinates are not physical quantities. Okay? So I don't want to talk about this a lot. There's a lot of work. A lot of you have probably heard about double field theory before. What I'm going to talk about is another interpretation of these non-geometric backgrounds, at least in certain settings, namely this 3-torus setting. And the suggestion is that, well, the observation was some time ago, again in the context of open string theory, that there's no consistent limit of an R-flux background that completely decouples open strings from gravity. Okay? In the B-field background, there is such a limit. But in the R-flux background, there is no such limit. And it was even suggested that, well, maybe the effective dynamics in these non-geometric backgrounds shouldn't be thought of as string dynamics. We should think of the fundamental degrees of freedom as being something different. And that's what I'm going to advocate here today, that we should really think not of closed strings in non-geometric backgrounds, but we should think of them as membranes, three-dimensional membranes with a boundary. The boundary of the membrane is your closed string. The membranes themselves see an ordinary geometric background, and what we'll see is that they see a doubling of the target space to the cotangent level, or the phase space. Okay, so a lot of flavor of this is what you see in double field theory, because we're doubling things up. We're not doubling with dual coordinates, we're doubling just by putting in momenta. And on the cotangent bundle, in phase space, the R flux is a geometrical object. It's just a free form in momentum space. Okay, so it has a geometric interpretation. And with this kind of arguing, we can quantize the theory. We're going to look at a sigma model, a topological sigma model. That's the analog of the Poisson sigma model. Okay? Once you look at the Poisson sigma model for open strings, the path integral for that sigma model reproduces Konsevich formalism for deformation quantization. That's going to be the idea. And the interpretation is that the membrane kind of has a double life. On the one hand, it's an open membrane, its boundary is a closed string theory, and the closed strings live in this mysterious non-geometric flux background. But on the other hand, there's a kind of closed open string duality that I'll talk about, where we can think of the membrane as inducing not a closed string, but an open string with what's called a twisted Poisson sigma model. And then the quantization of that Poisson sigma model will give this non-associative star product that I've been mentioning. Okay? No, not M theory, no. No, I wouldn't think of this as M theory. No, it's just, I don't even have any dynamics for this membrane, so I'm going to write down a topological model. Because the topological model is what I want to quantize. And I need a membrane. You see, the reason why the membrane comes in here is because I've got three forms and three vectors floating around. The Poisson sigma model can't accommodate for those.
Right. You can't have these structures in M2.
Yeah, I'm hesitant to say that this is an M2 grade. That's all. Especially since I'm being recorded. So. Okay, and so we'll get this non-associative star product, and it's non-associative, so there's a Jacobiator that you calculate for it, and that's going to give a quantization of this three bracket that I talked about.
So what happens to your membrane picture if you don't do the T-duality, which led you to the...
Yeah, it's a good question. It's a good...
The R-flux thing, if you don't do that by T-duality.
I don't know. We haven't... what I'm going to show you is I'm going to write down the most general topological membrane model, and I'm going to show you what that looks like in the geometric case, and then show you what it looks like in the non-geometric case. And that's where you'll really see the difference between them. I don't really know how to apply T-duality to this thing. But when I'm going to come to it now, it's going to be clear what the distinction is between the geometric and non-geometric cases. So I should ask if there are any questions, because now I'm going to start sort of doing a little more technical stuff. This has kind of just been what the talk's about, so you could almost leave now. This is what everything else is sort of technical stuff now. Are there any other questions? Let's move on. Okay, so we're going to look at this dynamically. Let's think about sigma models. Okay, we're going to think about topological sigma models. So these are not sort of physical theories. We're not going to have propagating degrees of freedom, but they're going to be models that we can use to think about quantization. And in some cases, for instance, with the Poisson sigma model, we can alter that model slightly to get a more standard sigma model with propagating degrees of freedom. So there's a whole general class of sigma models called AKSD sigma models. And that's, let's see, for Alexandrov, Konsevich, Schwartz, and Zabrody. Okay? So there's this very general framework for constructing action functionals using Batalin-Vilkovisky quantization, and there's a hierarchy of them depending on some natural number n, and at each level, the target space of that sigma model is a symplectically an algebroid. Okay? So I'm not going to explain what these things are, but they're vector bundles over a manifold with some additional structure. Okay? And we'll see some examples, but I'm not going to sort of give the general definition of what that is. But indeed, the best known example is of these class of sigma models is the Poisson sigma model. So we look at n equals 1. We look at a symplectic 1 algebroid, or just a Lie algebroid. And in particular, I want to look at something more specific. I want to look at the cotangent bundle over some manifold. And if M is a Poisson manifold, then the cotangent bundle has a natural structure of a Lie algebroid. But in any case, even if my manifold is not a Poisson manifold, I can go and write down this two-dimensional topological field theory using this general AKSZ formalism, and I get an action which looks like this. So the input here is a bivector field on the manifold M, which is our target space. The x's are maps from a two-dimensional manifold, could be open or closed, into the target space. And then these psi's are one forms on sigma 2, which are valued in the Lie algebroid, in this case the cotangent bundle. And that's a well-known Poisson sigma model. Now you could modify this model actually by putting in a kinetic term for these one forms. You just put a psi wedge star phi, a kinetic term for it there, and you could integrate out the psi's. They're actually just auxiliary fields, and then you just get the standard sigma model for string sigma model, where when you integrate out this term, you would have to invert this term and place the role of the B field. Okay, so you get a topological term from here that gives you the usual B field coupling of strings. Okay, so it's topological, easy modification using the sort of physical sigma model for strings. But why is this model interesting? Well, because it was realized in the late 90s that the Feynman perturbation expansion of this model reproduces Kontsevic's formalism for global deformation quantization. You can derive the star product and the whole, in fact, not just the star products, the whole sort of formality maps that Kontsevic developed in his in the late 90s. Okay? So at this stage, this theta is just any bivector, but on shell, meaning when I impose, when I take the BV charge, and I demand that it be nilpotent, I get a restriction on this. So the bracket here is the Shelton bracket of this bivector field, and this just says that the Shelton bracket vanishes. Shelton bracket vanishes. The Shelton bracket is the thing you calculate if you go and write down the naive Poisson bracket for this bivector field, and you try to calculate the Jacobi identity. The thing you get there is the Shelton bracket of this. So if that's 0, the Jacobi identity is satisfied, and this theta defines a Poisson structure on your manifold. Okay, that's the Poisson sigma model. It's the lowest member of this hierarchy, so now we'll go up one. Let's look at n equal 2. So we want to look at a symplectic Lie 2 algebroid, and that's the same thing as what's called a Courant algebroid. Okay? I'm not going to go through. There's a long list of axioms and their structure maps there. So again, it's a vector bundle over your manifold. It has a 2 bracket. It's got a metric on its fibers. It's got something called an anchor map, which is a map from that vector bundle to the tangent bundle over the manifold. And then there's a 3 bracket on the sections of this vector bundle that I think of as this 3, 4. So given those structure maps, you can write down, again, one of these AKSC sigma models, but now you have to increase the dimension of the world sheet. So every time you go up a level in this hierarchy, you increase the dimension of the source objects here. So the sigma 3 is now a membrane world volume, 3-dimensional object. And now I have sort of two auxiliary fields in the game. Again, I've got some one forms which live on sigma 3 and are valued in this Courant algebroid. But now I've got additional data. I've got these two forms which are now valued in the cotangent model. Okay? So this is called the Courant sigma model. Okay, and there was many motivations for studying this. I mean, I think in fact Hoffman and Park were trying to do something with M2 grains, but I don't think anything came of that. Okay, so that's that. That's a general sigma model, but what we're going to be interested in for the rest of this talk is what's called the standard Courant algebroid, which is just this generalized tangent bundle that we saw before. Okay, so we take the generalized tangent bundle, we pick some frame for the vector fields and one forms, and put the natural dual pairing on it. That defines the metric.
What happens now if you without the auxiliary field?
I'm going to talk about that, yeah. And of course, it depends on the nature of these structure maps. But that's what we're going to start. That's the game we're going to start playing now, is trying to integrate out these extra fields. And that's what we'll do first. So let's think about the geometric setup. So we'll look at the sigma model in the geometric case. So we'll take this standard Courant algebroid, and we'll twist it by a 3-form. Okay? Twist it by this. The twisting, as I said, these Courant algebroids have a bracket defined on them. In this case, the twisted bracket is called the Courant-Dorfman bracket. There's the formula. It's not a very illuminating formula, but the y's are vector fields, the alphas are one forms. And then this anchor map I talked to, the map to the tangent bundle, is just a natural projection of the generalized tangent bundle onto the tangent bundle. Okay, so this is a bit more illuminating. If you evaluate, the non-vanishing brackets are these ones, when you evaluate the natural frame for the vector fields in one forms. And now I'll split up my fields into components. So remember, the alphas were valued in this Courant algebroid. So if the manifold has dimension d, there are d directions that are tangent to the manifold, and then d directions which are cotangent to it. So that's the notation here. And then the sigma model I wrote down before, you put all these maps into that formula, and this is what you get. That's what we get. So what do we do now? Well, what we're going to do now is we're going to integrate out phi. Okay? So you integrate out phi, and that tells you that alpha, is equal to dx. And then we're going to get something well known. So we're assuming here that this sigma 3 is an open 3 manifold. Its boundary is some surface. We're going to, by hand, put in some coupling on the boundary to a bivector again. And when we do that, we get this model here. Okay? So the top line is just the action of the Poisson sigma model that we saw. And this term is if you think of this as a West-Zumino type term. And this is something called the H-twist Poisson sigma model. Okay? The point here is that everything involved here is, again, nice and geometric. I've reduced my membrane model to a sigma model on its boundary. So it's, again, a sigma model on a two-dimensional world sheet, and the target space is the manifold N. Okay? All reference to the Courant algebroid is gone from this picture. And again, you can look, go look at what happens to the BV charge and so on. And now what happens to this H flux is it gives you a twisting of the Schouten bracket. Okay? And that tells you that the Jacobi identity for this naive bracket that you want to write down is violated. But again, this is something that people studied a lot. There's a lot of literature on these. These are called twisted Poisson structures. Okay, so you lose the Jacobi identity, but as long as the violation is controlled by a 3-form, in this way, you can actually study these manifolds. Okay, so let me go back again and to understand what's coming up. We're going to go back to the sigma model in a moment, But to understand what's coming up, I want to just talk a bit more about this T-duality transformation, which takes us from the geometric H-flux background to this non-geometric R-flux background. So when we go from the H-flux background to the Q-flux background, the Q-space geometry is locally that of a vibration of two tori over a circle. Okay, that's the way I think of it, locally. Now the closed string world sheet I write with in this form, so it's just a cylinder with time coordinate sigma 0 and circle coordinate sigma 1. And as I take sigma 1 around the world sheet circle, the strings conwind around the base of this vibration, the base S1 of that vibration. Okay, so I'll call that winding number around that base P tilde. But what happens is, as you go around the base, so as the strings wind around the base of the vibration, you look at what happens on the fiber coordinates. Okay? And the fiber coordinates do not need to be periodic under this transformation. They only need to close up to an automorphism of that two-dimensional torus, so an SL2Z transformation. And that transformation is actually parametrized by the H-flux, and if you write the coordinates of T2 in some complex combination, then doing this periodic rotation just amounts to changing these fields by some phase. There's some phase factor that comes in. So the fiber directions are multi-valued, so we think of them that they have twisted boundary conditions as you pass through some point along the spatial circle. Now, the phase factor that you generate from doing this rotation is completely analogous to the phase factors you get when you look at open strings in a constant B field background. There you get phase factors because the boundary conditions for open strings get twisted. So what you do is you take the sigma model, you can quantize it to linear order in the H-flux, because to linear order in the H-flux you could neglect the back reaction of the geometry, drop the curvature, because the curvature is order H squared. So to linear order, you can quantize it just like you would in flat space, and the canonical quantization looks like just what you would get when you quantized open strings. So I'm not going to explain it. If you know the story, then it's exactly the same. So what you find are brackets. These are just the canonical brackets of the zero modes of the strings that look like this. So there's a non-commutativity. The Q space is non-commutative, where the non-commutativity is not only controlled by this flux, but closed strings have to wind around the base of this vibration to see non-commutative effects. So it's very different from what happens in the open string sector. But this is analogous to this non-commutative torus vibration that I talked about before. And these are just winding numbers, so they commute with themselves and they commute with the x's. So this is just basically a Heisenberg algebra, right? But now when you apply, the formal argument for what happens now is you apply T-duality now to this system. The Q fluxes map to R fluxes, you raise the index, and winding numbers turn into momenta. That's the rules of T-duality. So the right-hand side here becomes this. But this changes now, because the P tildes become P's, excuse me, and the P's are canonically conjugate to the X's. So you get this non-vanishing relation here. And that's crucial, actually, because of this relation here, you actually violate the Jacobi identity. If you write down the Jacobiator of this bracket, because of that relation there, you get a violation of the Jacobi identity in the coordinates. But on the cotangent bundle, I could think of this as a 3-form, and again, this is just a twisted Poisson structure on phase space, on the cotangent bundle. Okay, I'm not going to comment on that last sentence. So this is what was known in the literature from quantizing closed strings in these backgrounds. Now, this is just, I'll just quickly go through this. This is this, this closed open string life of the membrane. As I said, the string fields along the fiber directions are multi-valued. So I think of them as when I want to calculate correlation functions in the conformal field theory of my closed strings, there's a well-known way to think about this. So the fact that the fields are multi-valued means that you can think of this using orbifold CFT techniques. Okay, so these are multi-valued, these are things that we think of as single-valued on the orbifold, but they're multi-valued things on the covered space. Okay, so we insert a twist field there, and we create a branch cut. Now we take the world sheet, which is this cylinder, and we just put another direction. So in the picture here, I call this sigma 2. Okay, so this is the original world sheet. This branch point here extends to this interval, gives me a branch cut. Okay, so there's no time in this picture. And then there are two reductions you can do of the membrane theory. You can just forget about the extra dimension, do a dimensional reduction in the path integral. So restrict the domain of the path integral to fields that are independent of sigma 2, then you just get the ordinary closed string dynamics. But on the other hand, when we go and start manipulating the Courant sigma model, whenever we do these integration by parts whenever we integrate out auxiliary fields, at some point we come across an integration by parts, and of course, we can apply Stokes' theorem when everything's nice and smooth, but as soon as we have multi-valued fields, you get non-differentiable contributions from the fields along this cut. And the path integral in that case reduces to something that effectively looks like an open string. That's what we're going to do explicitly. So this is not rigorous, but this is the way we're thinking about the membrane here. So on the one hand, it induces closed string dynamics, but on the other hand, we can think of it in terms of open strings. We have to do this because if we want to quantize eventually the way I'm going to explain, we need to have an open string sigma model at the end of the day. So you see, the problem is that we've got a membrane, and we want the boundary of the membrane to be an open string rather than a closed string. So you want the boundary of the boundary to be non-empty. And of course, the only way you can do that is if you make this thing somewhat, well, for me it's exotic. You have to work with manifolds with corners, right? That's what these things are called, where the boundary of the boundary is non-empty. Okay, but I don't want to do that here. I prefer to use this physical intuition. Okay, so now finally we'll go and look at the sigma model in the non-geometric case. So again, take the standard Courant algebroid, but now I'm going to write down the structure maps appropriate to not a three-form background, but a trivector background. Okay? So there is a bracket in there are structure maps known in the literature due to Reutenberg. So there's the Reutenberg bracket. Okay, again, it's perhaps not very illuminating. What's illuminating is when you evaluate them on a frame. So these are, again, the only non-vanishing ones. These look somewhat opposite to what we had in the geometric background. In the geometric background, we had vector fields here, and then the H-flux there. So this is where sort of covariance becomes important, that you write your indices in the right place. It's really, really important here, because then you can really see what's going on, and then there's only one way to contract things. Okay, so I take all that, I put it into the Courant sigma model that I had before, and again I integrate out these phis. Integrate out the phis, and you get something that looks like this. So there's this term here, which is now on the boundary of the membrane, but this term here does not have any natural two-dimensional interpretation yet. Okay? This is an intrinsically three-dimensional quantity, because remember these were one forms that were valued in the Courant algebra. Okay? Now I've put an extra term here, which is non-topological and involves the Hodge star on the world sheet. And I need to do that because this model, the first line is actually inconsistent with R non-zero if you look at the equations of motion. So you just have to tweak it a little bit by putting in this non-topological term. So that's a general statement there, but now if I look at constant R flux and a constant metric on the in the target space, then I can integrate out. I can look at the equations of motion for the axis, and that tells us that the sides are closed. Okay, so at least locally, I can take these sides to be exact. And for a suitable choice of world sheet, you can assume that these are exact forms. Okay, and I write them in terms of capital P's. I'm going to think of them as momenta, because I always follow my nose with the indices. Momentum has lower index. And this is what we end up with then. So once you do that, these sides are now exact forms. You substitute them in there, and now you can apply Stokes' theorem and reduce this thing to the world sheet. So it's no longer an intrinsically three-dimensional quantity. And if you just fiddle around with it a bit, you can write it in this form. So the x's with the capital Latin indices denote components tangent and cotangent to the target manifold. Sorry, not tangent and cotangent. These are just coordinates in the tangent. The local coordinates in the tangent bundle. Theta is written in terms of the R flux like this. There's some effective metric that appears up there. But the whole point is look what's happened to the target space. The target space of this model is not the manifold M, it's the cotangent bundle. So this is just the Poisson sigma model now, twisted Poisson sigma model, but on the cotangent bundle. And this bivector there is exactly what appeared in these brackets that I wrote down a few slides ago for the R flux background. Okay, so this is a derivation of those brackets. So again, it gives us a twisted Poisson bivector, and now the R flux has a natural interpretation. You can think of this now as a gerb in momentum space. That's one way to think about this guy. Okay, and so again, the non-commutativity as usual is controlled by the bivector and the non-associativity, right? The Schouten bracket, I'm going to call this quantity capital pi, and that's completely controlled in the coordinate directions by the R flux. Okay, but that's a dynamical model, so the membrane explains both how we get the standard geometric background, the H flux background, and it also shows how these newer non-geometric backgrounds come into play here. Right. Okay, are there any questions? I'm going to talk now about quantizing this. So now, this is why I want to think of this now as an open string sigma model. I'm going to drop that non-topological term just by assuming that the R flux is much bigger than this metric. And then I've just got a Poisson sigma model with the target space is the cotangent bundle of my manifold. And now when I quantize this model, I know from Cattaneo-Felder that I get the Kontsevich formality. Yes?
This one, does it work also for if you replace theta by a generalized complex structure? I mean, there were some attempts by Zucchini, for example, to construct a topological sigma model for generalized complex structures, which look very similar, but they have mixed dx eta terms.
That's right. So you can, yes, so there's some work. So if you go back to the Courant sigma model, of course I've only looked at two extremes where you've got an H flux and an R flux, but you can actually ask what happens if you put in the most general combination, you put metric flux and Q flux, and I don't know the answer what happens there. It looks a bit of a mess, but you could do it in principle, but I'm not sure what the answer is. And you're right, I think Zucchini did do some stuff.
Yeah, but I think even himself was not convinced by that. I mean,
don't know what his motivation is. I mean, you see, ultimately what you'd like to go and do is just take that membrane model, the Courant algebra, the Courant sigma model, and quantize it. That's what you'd like to do. And people tried that, over 10 years ago, and it's just a big mess because you have these higher Lie algebroid symmetries, right? The Courant algebra is a Lie 2 algebroid. So it's like, doing the quantization of a gauge system where you have to include not just ghosts, but you have ghosts for ghosts, and then ghosts for ghosts. You have this hierarchy. And it's just a total mess. So we didn't even want to try to attempt to quantize the membrane model, but now we've reduced it here, and we can go and quantize it. Okay, so I'm going to be very sketchy here because the Kontsevich stuff, it's hard. It's really that. But the point is that when you quantize that sigma model, you reproduce the graphical expansion for deformation quantization. Deformation quantization is based on something known as the formality map. The formality map is a prescription which takes any collection of multi-vector fields, that's what these curly X's are, and maps them into a collection of differential operators. Okay? And the prescription has a graphical interpretation, so that's what the sum is here. This is a sum over all what are called admissible graphs, and you can calculate these things. Okay? There are these weights W gamma there. Kontsevich gave a prescription for how to calculate them in terms of integrals over the hyperbolic half plane. So, you go look all this literature up and you can do it. And the point is that the Kontsevich's approach and the Cattaneo-Felder approach do not require that your manifold be a Poisson manifold. Okay? I mean, that's what everybody applies it to usually, but it allows for having this three bracket there as well. And in fact, the formality map gives you a way, you could take any collection of multi-vector fields, so you can also take a tri-vector field and substitute it into this formula and get out something meaningful. And that's what we do. So if we substitute in the bivector fields, so these are just representative sketches of what the graphs sort of look like. So the graphs typically look like this, where you imagine that all this is on the upper half plane, and on the real axis, the boundary of the half plane, you place the functions that you want your multi-vector fields to act on, and then you draw the legs of the multi-vector fields in this form. Okay, so if I apply formality to a bivector, then I just get a star product. I get a binary operation on functions, and then I'll denote by this. And if I take this trivector, pi, stick it into the formality map, I get an operation, a ternary operation, where I take a triple of functions, and I calculate something like this. So I'll call this phi. So you go, and this is where the PhD student comes in to go and look at all these graphs and do all these horrible calculations, and then come back to you 2 months later with a nice answer. Yeah.
And is the triple product related to the Jacobiator?
I'm coming to that. The answer is yes. But it's not immediate. So right at this stage, this is just some ternary operation. There's nothing telling you right here that this is related to that. But that is indeed going to be the case. Okay. So. Yeah, okay, these are just some words at this stage because I just don't have time to explain it. But, what these formality maps do is they relate, for instance, Schouten brackets of multi-vector fields to what are called Gerstenhaber brackets of multi-differential operators. Okay, so that's what this symbol G is there. And so there are these formality conditions that Kontsevich derived. The first formality condition is when you look at the Schouten bracket of the bivector. You put that into the formality relation, and it just tells you, indeed, that this three bracket is the associator for that star product. It's not immediate from the definition, but it follows from these formality Now, if you take the Shelton bracket between this trivector pi and the bivector theta, this gives you another formality condition. And if pi is constant, so in the case of a constant arc flux, for example, you can write that condition in this form. Okay? And to lowest order, you see that this pi, if it's a constant trivector, you can think of this as defining a Nambu-Poisson structure. So just a generalization of a Poisson structure to a constant trivector. And then the version of the Jacobi identity is replaced by something called the fundamental identity. And also the Leibniz rule for the 2 bracket is replaced by a Leibniz rule for the 3 bracket. And that's what this thing turns out to be. It's the lowest order in the deformation. So also these this formalism, this sort of deformation quantization formalism seems to give away to quantize Nambu-Poisson structures, at least constant ones. And this is an open problem. It's been a big open problem since the days of Nambu from the early 70s on how to quantize higher order Nambu-Poisson structures. So this might do it. But let me now come to the gist of it. So what I've said is fairly general so far, but now we can go and look at the R flux background, and we can write down explicitly what the star product is. Okay? So so those of you who know your star products go, well, that is almost something I could have guessed, and maybe you could have, but this is what you get from looking at all the graphs in the Kontsevich expansion, realizing that most of them go away, and then the classes that are left you can actually sum up and write as an exponential of some nice-looking Lie differential operator. Okay? That's constant R flux, yes. So you get this formula here, so inside the big brackets, you've got some bidifferential operator acting on your functions, and the dot there just means the multiplication, the pointwise multiplication of the things in the tensor product. And I put a subscript p there because you can understand why this thing is non-associative. If I replace the p variable there with a constant p tilde, then this is just the Moyal type star product, meaning it's just something that's given by a constant commutator between your coordinates. Okay? And the non-associativity comes about when I let p become dynamical. So I go away from the slices of constant momenta, because the whole non-associativity, you see, comes about because, so these tilde derivatives are momentum space derivatives. And it all comes about because when you calculate a triple product, these d tildes start acting on the p's. So this is why I call this a dynamical non-associativity, because it's really sort of you turning on the momentum, and that's what's doing it. And the 3 bracket has a really nice form. You can write it down in this closed form like this, in terms of some tridifferential operator. And then there are various nice properties the whole formalism has. For instance, there's this nice trace property. And all of this that we derived from these, sigma model arguments and the Kontsevich formalism agree with formulas that people postulated based on conformal field theory calculations in closed string theory.
Can I ask a question?
Yeah.
If you were to include a Villedon on the closed string side and a P field and T-equalize it until you get to this non-geometric phase, where would it show up on your open string side?
Yeah, I haven't thought about that. I haven't thought about putting it on these. Yeah, it's a good question. Right, I'm just about out of time, so let me just make 2 comments two mathematical comments about other ways to think about these structures, which are useful in their own right. So one is this notion of a kind of categorified quantization. So if we have a Poisson bracket, that's also that's also a Lie bracket. So it's a linear Poisson structure. Another way to reproduce Kontsevich's quantization is to do what's called convolution quantization. Okay, so the idea is you integrate your Lie algebra to the Lie group, you do a convolution product in the Lie group, and then pull it back down to the Lie algebra. And that turns out to be the same as the Kontsevich formalism. So what do we do here? We don't have a Lie algebra anymore because the brackets, the Jacobi identity is violated. But what we do have is we have a structure of a Lie 2 algebra floating around. Okay, so Lie 2 algebra, a Lie 2 algebra in a lightning flash is just going to be this thing where we relax the requirement that the Jacobi identity. Okay, so if we take this, remember what we had in the R space, we had brackets like this where I don't use dynamical momenta, but I use these winding numbers. Then, okay, again, I don't have time to define all these things, but if you know this stuff, my Lie 2 algebras can be thought of as two-term L infinity algebras with some structure maps that look like this, and then there's a 3 cocycle which classifies this. So G is this Lie algebra up here, and that's exactly what gives us this R flux. Not every Lie 2 algebra can be integrated to a Lie 2 group, but in this case you can. It integrates to this thing, and then the associator integrates that. And the whole point is if you, so this is in our paper if you're interested in looking it up. The whole point is you have this notion of a convolution type quantization, and it exactly reproduces the Kontsevich approach. Okay? So there's sort of stuff to do here. There's a whole new direction in categorified quantization one could think of. And then the final thing I want to just mention is that, well, another way, I mentioned these twist deformation techniques, where you take some Lie algebra that you think of as symmetries on your space, you look at the enveloping Hopf algebra of that Lie algebra, and then you deform it in a way that's compatible with the way you're deforming your underlying space-time. So to reproduce our quantization, our non-commutative structure, we look at a non-abelian Lie algebra that's generated by these vector fields there on phase space. And you might ask, what are these things? Well, these M's here are things which generate the non-local phase space transformations of quantum mechanics that are called Bob shifts. So you take your x coordinates and send it to x plus some combination of momenta, linear combination of momenta. And that's called a Bob shift. Okay, so that's what that is. And then you can look at, again, the enveloping Lie algebra, construct a non-abelian twist, which looks like this. Okay, so it looks very similar to the bidifferential operators I have, but it's not a cocycle. So usually this thing, the twisting object satisfies a cocycle condition, which is equivalent to the associativity or co-associativity of anything that you're twisting. So again, it's not a cocycle, it's a cochain, and that cochain has a boundary in the quasi-Hopf algebraic framework that looks like this. And again, you can think of this as a kind of categorified quantization, because what I do is I look at the category of quasi-Hopf module algebra, so I just look for representations of this quasi-Hopf algebra, the thing that I twist with this, and then you can translate this into a categorical framework where the category that you're dealing with is not a strict category anymore, but it's a semi-strict category because it has there is an associator, but the associator is non-trivial. So I don't have time to say anything more about that, but I think I'll stop there.
Any questions?
Do you know anything about representations of those two algebras from the previous?
These things. Representations of them, no, I don't know. I don't know. All I know is that in this case, I mean, this is an example of it's a quadratic Lie algebra, and every quadratic Lie algebra, it's a quadratic Lie 2 algebra. Sorry, the Lie algebra I start with is a quadratic Lie algebra, so the associated Lie 2 algebra can always be integrated to a Lie 2 group. That's all I know about it. But so Baez and other people might have written something about the representation theory. I don't remember, but I certainly don't know anything about it.
So, in your case, the non-associativity is not that bad, right?
Sorry, say again?
The non-associativity is not so bad in the open string case because there is this multi-associative structure. Also something like that?
Yeah, that's a good question, actually. It's something we played around for a while, because if you do look at the closed string correlation functions, they do involve the same type of dilogarithm functions that you see in the open string case. But no, we didn't succeed yet in understanding those in some terms of homotopy associative structure. But yeah, that was indeed a natural question. You do see the same structure there, but it doesn't seem to work as nicely.
So I didn't see any pi showing up in the definition of your formality maps, but then it showed up in the associators. So
Pi, capital Pi?
capital pi, yeah.
It was defined, it's here, right? So pi, in this formula, pi is any trivector.
Oh, okay.
Okay? And
It's not some fixed trivector.
it's not, but in the R-flux background, it's this. But that in the Kontsevich picture, this is just a general prescription for inserting a trivector.